Hello everyone, good morning. Thank you for being here. Today I am going to talk about a critical issue, the efficiency and the lack of trust in your current carbon credit markets. Today I am going to talk about a critical issue, the efficiency and the lack of trust in your current carbon credit markets. We'll be exploring a novel solution that tackle this problem head on by integrating two powerful technologies using blockchain to create a transparent and efficient trading system and using machine learning to ensure the allocation of those credits is both automated and most importantly accurate. The problem with the carbon markets. The problem with the carbon market is lack of transparency, fraud, and misallocation in accurate allocation. So why do we need a new system? The current carbon markets, while well intentioned, are fundamentally flawed. We have identified three core problems. First, there is a serious lack of transparency. The entire system is built on opaque registers and slow manual verification process, which creates widespread mistrust and massive operational inefficiencies. This opacity is also create a breeding ground for fraud and misallocation, with double counting being a rampant problem. In fact, some research indicates that a staggering 75% of certain national credit might not represent any real environmental benefit. Finally, the way credits are allocated is broken. It's often based on manual, survey-based methods that are slow, expensive, and error-prone, failing to capture the true drivers of emissions and making a fair allocation almost impossible. Slide 3, related work and research gap. Related work and research gap. We are not the first to look at this. Of course, existing research confirms the drivers of carbon emissions are incredibly complex and vary significantly from one nation to another. We have also seen purely conceptual blockchain methods for trading, and we have seen machine learning used to forecast emissions. But there is a critical research gap that we identified. No one has yet created an empirically validated framework that fuses high accuracy ML prediction directly with on-chain smart contrast. There is no existing system that allows for the fully automated, transparent, and truly data-driven issuance and allocation carbon credits. The slide for the solution, a hybrid framework. The solution hybrid framework, our solution is a hybrid framework that brings these technologies together. First, the blockchain creates the decentralized, immutable, and transparent ledger that the market desperately needs, directly solving the problem of trust and transparency. Second, smart contracts, which are self-executing agreements on the blockchain, automatically manage the entire credit lifecycle from issuance to retirement based on predefined rules. The innovation lies in what triggers this contrast. We use machine learning to accurately predict per capita carbon emissions. The prediction served as the reliable, variable, and data-driven trigger for the smart contrast. As the diagram shows, the predictive models feed their outputs into the blockchain, which in turn triggers the smart contrast to confirm the carbon credit allocation. The result is a system that finally ensures trust, accuracy, and efficiency. Methodology, data, and models. To build and validate this framework, we needed a robust methodology. For our dataset, we used to Global Carbon Budget 2022. Now, for a system like this that will have financial and environmental implication, data integrity is paramount. We couldn't risk imputation bias from filing in missing data. Therefore, we perform a strict complete case analysis, removing all complete records. This left us with 1,551 high quality complete reservation to train our models. We then selected and tested two powerful machine learning models, random forest. This is an assembled model that is highly robust against overfitting and is excellent at identifying the importance of different features, support vector regression, We choose this kernel-based model for its proven effectiveness in capturing complex non-linear relationship in data. The key result, model performance. After training and testing both models, the results were not even close. As you can see from this table, the random forest model was overwhelmingly more accurate. It achieved an R squared value of 0.98, meaning it's explained almost 98% of the variance in the data. Compare that to the SBRS 0.76. But most importantly, look at the error matrix. The random forest mean squared error was 91.7% lower than the SBRs. This level of precision is not just an academic win, it is absolutely vital when you are building a system that relies on financial and environmental integrity. The random forest model is the clear winner. The result, random forest accuracy. The scatter plot shows you why the random forest model is the clear choice. On the horizontal axis, you have the actual per capita emissions, and on the vertical axis, you have our model predictions. That red dashed line represents a perfect 1-1 correlation. As you can see, our data points are clustered incredibly tightly around that line. Our analysis of the residuals, the errors, also confirms the model is robust, consistent, and has no systematic bias. This proves the model is highly accurate at all emission levels, making it the ideal and reliable trigger for our automated allocation system. Result, support vector regression limitations. Now for comparison, let's look at the SBR model. The difference is night and day. You can see significant scatter all over the plot. The model is clearly struggling to make accurate predictions. Our analysis showed it was especially bad at predicting and mid-range emissions, that it is awkward increased as the emission values got higher. This model is simply not reliable and is completely unsuitable for a high integrity framework like the one we are proposing. The discussion. Key emission drivers from RF model. The random forest model does not give us accurate predictions. It also tells us what factors are most important for making these predictions. This is crucial for policy. Our model identified three primary drivers. First, gas flaring at 21.3%, which was the most important factor, highlighting the massive impact of industrial process waste. The second, the total capita ratio at 21.2% as a feature we engineered that serves a key metric for a nation's emissions efficiency. And the third, oil dominance at 14.2%, which emphasized that the specific composition of a nation's fossil fuel use is a critical predictive factor. This shows our model is picking up on real-world actionable drivers, which further validates its use. So, conclusion and key contributions. So to conclude, what have we established? First, we identified a super model. The random forest model with its 98% accuracy is a vastly superior and highly reliable predictor for carbon emissions. Second, we have proposed a viable framework by using this high accuracy ML model with a blockchain based system of smart contrast. We offer a viable, transparent, and automated solution that directly addresses the integrity issues in modern carbon markets. Finally, the data-driven impacts of this system is clear. It is enhanced stakeholder trust, dramatically reduce the potential for fraud, and for the first time aligns the allocation of carbon credits with data-driven variable emission sources. So, the last one, questions. Thank you very much for your time and attention. I'll be very happy to answer any question you may have. Thank you. This is Arafat Islam. That's my presentation for today. Thank you.